Okay, so in the last video, I showed you how to measure the angular separation of a moon from its planet and how this angular separation changes with time. So we collected a data set. In this video, we're going to take that data set and I'm going to show you how to plot it and how to fit a model to it. And using this model, we'll be able to extract orbital parameters, such as the semi-major axis, the moon's orbit around the planet, and its orbital period. So I'm going to share my screen. Okay, here we are back at the graphing tool. We learned how to use a little bit of this in a previous video. We learned how to use the curve plotting option. For this task, we're going to switch from curve to moon. So some things are different here, but some things are the same. For example, we have a data table. In this case, we have Julian date as our x value and angular distance or angular separation measured in arc seconds as our y value. Now, when you first switch to this option, you'll see generic data plotted here. And we're going to want to get rid of that and put your own data in there. So you can get rid of it just by highlighting it and deleting. Now, in the previous video, I recommended as you recorded your Julian dates and your angular separations in arc seconds, I recommended that you put them into a spreadsheet. That makes it easier to copy and paste into the graphing tool. So here's my spreadsheet. So I have the Julian dates here, which are large numbers beginning with 2, but make sure you have some decimal points there. That's a fraction of the day. And here we have the angular separation in arc seconds. Just make sure the whole number is there. Sometimes when you paste something into a spreadsheet, it may go into scientific notation, or if the column's too, such as that, or if the column's too small, it will just show asterisks. You want to expand it so you have the entire number. Copy, Control C, paste it into the table, Control V, and if it needs to add extra rows, it will. Okay, so we've gotten rid of the fake data, we've put in the real data, and before we fit the model to the data, let's get our title, let's get our axis labels correct. So the title is what we're plotting, and we are plotting the angular separation of Titan from Saturn. At least that's the data I collected. If you did a different planet, you will have a different moon, and consequently you will have a different title. So be sure to make that descriptively correct. And our x-axis, this is time, measured in Julian date, or you can just write Julian date, either is acceptable. And the y-axis, that's our angular separation. And don't forget the unit, it's measured in arc seconds. And since we only have one data set, you can just call that data if you want. Or you can label it Titan, or I'm just going to leave it as data, but that's up to you. And then the last thing we have is the model. That's the blue curve here. And clearly it's not going through the data at the moment, but we can control that. We have 4 sliders here. The first is for semi-major axis. So you can see as I move this slider, it can get bigger or smaller. And so what this is showing us is a model for how far the moon is from the planet. This is the moon moving farther and farther away. And then it starts moving closer and closer. And this is where it would pass by the planet. If it passes right in front of it, the angular separation is 0. Then it's moving out on the opposite side. So the orbital period is not one of these, but 2 of these bumps is how long it takes to go completely around and back to where it was. So let's adjust the semi-major axis to kind of match the height of the data. The orbital period, I'm going to lengthen it, kind of match this pattern here, coming up and down and back up, kind of has the same flow. The phase shifts it left and right. So you see I'm shifting it onto the data. And then you can control the tilt. If we're viewing the planetary system edge on, the moons will pass directly in front of the planet and we'll have zero separation. If we're viewing it face on, we'll see the moons going around and around the planet, but never getting any closer or any farther away. Most likely we're somewhere in between. So that's not a bad first guess. And then what we can do is we can adjust the parameters to really get it in there nice and tight. So let's see here. The orbital period's a little bit smaller. Shift it a little bit. That's pretty good right there. But spend some time. Try to get as close as you can. And sometimes the adjustment with the slider is a little too coarse. And so you can actually type in numbers here to do fine adjustments. Okay, so that's a good fit right there. And you want to do a couple things. You're going to want to save this onto your computer and upload that into WebAssign. Also, in the WebAssign lab, you need to know the semi-major axis in arc seconds. So here it is. This is the maximum number of arc seconds that your moon gets away from your planet. And the orbital period in days, and here it is. Now, I was lucky here. I got all 14 of my images back, and that makes this pattern very easy to see. If you didn't get the full complement of 14 images, it may be a little bit tougher. If you started late, you may only have 4 or 5 or 6 images, and that can make it very difficult to fit this curve if you have a small number of data points. In that case, what I recommend you do is give it your best attempt, but then go check the orbital period. Go to Wikipedia, look up that moon, and find its orbital period, and that will tell you whether you're in the right ballpark or not. Adjust it as you need to and refit, getting it as close as you possibly can. Okay, that's it for this video.